To describe wave motion, we will need to describe the following terms. So we're going to describe key terminology. Simple harmonic motion. This is abbreviated mostly in physics texts by the word, the acronym SHM. So when you hear SHM in physics, it refers to simple harmonic motion. We will need to describe terminology like displacement, amplitude, velocity, acceleration, of course, which derives from velocity. Other key terms are period and frequency. These are related. And then we have the two systems that are commonly used to describe simple harmonic motion or oscillations are the mass spring system and the simple pendulum. And then the second part, we have wave motion. Here we have primarily two types of waves, transverse and longitudinal. And then wave phenomena as this diffraction, interference, standing waves, resonance, so these are some key terms that we will need to describe, we will need to understand to be able to describe, wave motion and oscillations. And to conclude this section, we're going to talk about sound also. So sound. And other sound, we'll look at the sound intensity and how it's measured. And then sound intensity levels. Okay, so I think these are the key topics for module 1. So let's begin with the discussion of, each terminology or each term as pertains to oscillation. So the first concept is that of periodic motion. So this describes any back and forth motion along the same path with each, let's say, vibration taking roughly the same amount of time. So back and forth motion. Along the same path. With each, you could say each back and forth motion or each cycle taking the same amount of time. Okay, so this is known as periodic motion. So imagine something tied to a spring. If you displace it slightly, you would see the mass go back and forth, and the vibrations would take roughly the same amount of time. So that is a description of periodic motion. And the cycles of motion, the back and forth, is called vibrations. So that's another term that is used. So having described periodic motion, what then is simple harmonic motion? So simple harmonic motion is simply a motion in which there is a restoring force that is proportional to its displacement from its equilibrium position. So motion in which there is a restoring force that is restoring force that is directly proportional to its displacement from equilibrium. And equilibrium position here refers to the state of the system when it's not disturbed. So when, in the case of a spring, when the spring is neither stretched nor compressed, it is said to be at equilibrium. In the case of a pendulum, when it's hanging freely, it's not displaced on either side, that is known as equilibrium. So when you displace it from the natural resting point called equilibrium, and then let it go, it will swing back and forth. And it's swinging back and forth because each time it goes past equilibrium, there's a certain force that is pulling it back to the equilibrium. But because of momentum, the mass will overshoot equilibrium, and then the restoring force will pull it again back towards equilibrium. So the motion keeps on repeating back and forth. That's why the necessary condition for simple harmonic motion is that there must be a restoring force. So that's the very first condition. So there must be a restoring force, and then the second condition is that it has to be directly proportional to the displacement from equilibrium. That means if these two conditions are not met, then an object may oscillate, but you wouldn't characterize that as simple harmonic motion. It's only simple harmonic if there's a restoring force, and then the restoring force is proportional to the displacement from the equilibrium position. And just for emphasis, we're going to define equilibrium. And this is simply the state. So for a spring, so the state of the system when it is not disturbed. So for example, for a spring, let's say, sorry, example, when a spring is neither compressed nor stretched. So it is said to be in equilibrium. Another example is the pendulum hanging freely with no displacement. Okay, and just to illustrate this, so you could have so this is a mass attached to a spring, and let's assume that the surface is frictionless, so there's no frictional force. So when this spring is neither stretched nor compressed, then you would call this position so this is the equilibrium. Similarly, for a pendulum, so this point is also the equilibrium. So to set this into simple harmonic motion, all you would need to do now is to, pull the pendulum to the sides and let it go, and then you oscillate back and forth along this point. Similarly for the spring, you need to pull the mass either to the right or push it to the left, and once you let it go, you begin, swinging back and forth, and you call that, oscillatory motion, periodic motion, and simple harmonic motion if the two conditions in the previous slide are met. If there is a restoring force, which is proportional to the equilibrium position. Okay, so let's continue with the definition of the terms. So another key term is displacement. So what is a displacement in this case? It's simply the distance from the equilibrium position okay, so distance from the equilibrium position to the current okay. So the displacement is the distance from equilibrium position to the current position, or the change in position from equilibrium to where the object is currently located. So let's go back one slide. So in these diagrams, the displacement of the objects are zero because both are located at equilibrium. So there's no change in position from equilibrium. But if we were to, let's say, pull the spring to the right, then now we would have a displacement. So from here to about there. Okay, so the green arrow would represent the displacement. So if we went ahead and labeled this x sub O, and then label this x, so the displacement would be the final displacement minus the final position minus the initial position. So let's say this was a number line and the object was located at coordinate point 7, and it was displaced to a new coordinate 10. So the change in position will be 10 minus 7. So that gives us a displacement of 3 units. Okay. So when you hear the word displacement, remember this is a measure of how far the system has deviated from the equilibrium. And all these terms are very critical because going forward, we're going to be using these terms to describe different aspects of oscillatory motion. And if you didn't properly understand what the terms mean, then you may be lost when we discuss more complex, concepts. And the next term, which builds on displacement, is amplitude. And of course, displacement is measured in meters, SI unit, amplitude measured in meters, that's SI unit. And the amplitude is simply the maximum displacement again from equilibrium. Okay, so displacement is a measurement of how far the system has gone away from equilibrium. So it could be any point, but among all the displacements, there will be the largest one, and that largest displacement is called amplitude. Okay, so if you keep displacing a system from 0 to a certain value, so and all of the values between 0 to the maximum value are just called displacements, but the maximum value, the furthest point that the system goes, is called the amplitude. And for a mass spring system or for an oscillatory system, there are always two amplitudes, because you could displace the system to the left of equilibrium, that's negative. You could displace it to the right, and that's positive. So like let's go back in the case of the spring, one could displace it to the right, and one could also displace it to the left by the same amount. So those will both be displacements. So this is equilibrium. And if this was the maximum the spring went, then maybe I should just get this to the next page. Okay, so I'll place it here. Okay, so erase this. So this is my equilibrium, and this will be the amplitude, and this will be another amplitude here. So I could set this into motion by compressing this to the point minus A, or stretching it to the point A. Those are both amplitudes. That's the furthest displacements from equilibrium. So if this was a number line and the equilibrium was 0, then the amplitude could be, let's say, 5 units to the right, that's plus 5, or negative 5 units. Okay, so let's continue discussing the terms. We have potential energy. So potential energy is simply energy stored as a result of the state of the system. And in both cases, in the case of simple harmonic motion, the state is the displacement from equilibrium. In other words, if a simple harmonic oscillator is not displaced from equilibrium, then there is no energy stored. Like in the case of a spring, if the spring is not stretched or compressed, it doesn't have any ability to cause motion, so it has no energy. But once you stretch it, the stretching action stores energy in the spring. And when you let it go, it has ability to move, to cause motion. So similarly, when you compress it and let it go, it has the ability to cause things move. And that is, that is used in many technologies, like to project things. You can have a large, a very strong spring, that compress it, and then put a projectile in front of the spring. Once you let it go, the spring will shoot the projectile. So the energy to shoot the projectile comes from the energy that was stored in the spring when it was compressed. And the potential energy, we're going to come to that. Let's just define the terms now before I introduce the equations or the mathematics behind that. We also have kinetic energy. So kinetic energy is the energy of a mass as a result of its velocity. So energy of a mass, or energy of a body. Remember, body in physics simply refers to any object that has mass. So energy of a body as a result of its motion or its velocity. Okay, velocity is the rate at which the displacement of the object is changing. So if an object's displacement is changing, then it has a velocity. If it doesn't have a velocity, if it's standing still, then it has no kinetic energy, because kinetic energy depends on the velocity of the object. Okay, so more terms. We have period, and the period here is the time. It's commonly denoted by T and measured in seconds. So the unit is S, the symbol is T. So kinetic energy, the symbol is kinetic, Ke. Potential energy, the symbol is Pe. So when you see these terms, be aware that it's referring to potential energy. This is measured in joules, and this is also measured in joules. So periods measured in seconds is time to complete one cycle. The time to complete one cycle of motion. So in the case of a spring, if you pull it to the right and let it go, the time it goes all the way to the left and then comes back to where it started is called one cycle. So that is the period, the time it takes to leave from where it started all the way to the other end and back to where it started. For a pendulum, the same thing. If you pull a pendulum to the right and let it go, it will swing to the other extreme to the left and then come back to where it started. That is also one cycle. It's one complete to and fro motion. Okay, so maybe I should add that to the definitions. So one cycle is, one complete to and fro motion. Okay, and then we have the term frequency. And as the name suggests, is literally, how frequent the system completes cycles. So this is denoted F and measured in hertz or seconds or per seconds. Okay, so hertz is also denoted Hz. So if you tune into, if you look at your radio signals or TV signals, you see different frequencies. You have the kilohertz, the megahertz frequencies range, and so on. So hertz refers to the number of oscillations per second. So number of cycles completed in 1 second. And if we combine this with the definition of periods, remember period is how long it takes to complete a cycle. Now, if you wanted to know how many cycles will be completed in 1 second, then you will just need to divide 1 second by the period. So that'll tell you how many cycles have been completed in 1 second. So for that reason, there is this simple relationship between period and frequency. Frequency is equal to 1 divided by the period. Okay, that's one of the first equations you need to take note of. So if you know the frequency, then that means you know the period, right? Because the period is just the inverse of the frequency, and the frequency is the inverse of the period as well. So T equals 1 over F. Simple arithmetic, right? If you flip both sides, then the right-hand side becomes T, the left-hand side becomes 1 over F. If you flip it again, you come back to F equals 1 over T. So when solving problems, be mindful of the fact that once you know F, then indirectly you know T. So there may be a problem where they give you the frequency, but what you really need to solve the problem is the period. Now, some students will stop there and say the instructor didn't provide the period. But if you know F, you should know T, because one is just the inverse of the other. So be aware of this, relationship. Okay, so to complete the terminology, let's look at the simple pendulum. So a simple pendulum is simply a mass attached to the end of a string or rod that is free to oscillate back and forth. So let's say this is support. And then I have a mass attached to of course, I'm going to have the equilibrium. So this is equilibrium. And then, of course, the displacement. That's the displacement. And since this is not really a straight line, we're not going to use x. So maybe let's use a different variable. I'll just label this as 0. You understand what I mean? So this is 0. And then we'll call this S. S is the symbol for arc length, because this is an arc. So S An arc is simply a segment of a curved path. Okay. So you could also describe a pendulum in terms of the angular displacement. So the angle between the equilibrium line and the length of the pendulum. So the length of the pendulum is described as the distance from the point, the support, to the center of the pendulum ball. And you're going to do a lap on this, so you find this information useful for that. So L is the length of the pendulum, and in the lab you measure L from the point where the pendulum is supported to the center of the pendulum ball, the ball or the mass that is attached to the pendulum. And so for a pendulum system, the periods of this system will be 2 pi times the square root of the length of the pendulum divided by g. And since frequency is 1 over the period, the frequency will be 1 over, you just flip this equation, 1 over 2 pi, flip what you have in the square roots, you have g divided by L. So that's the period and frequency for a simple pendulum. So if you know the length of the pendulum, then you can find the period and frequency, because g here is a constant. So g is equal to acceleration due to gravity, which is approximately 9.8 meters per second squared. So that's a known constant. Then L is the length of the pendulum. So in a lab, if you measure the length of a pendulum, and you can predict the period or the frequency by this formula, and you can actually measure it using a stopwatch to compare if the values are correct. Okay, so period and frequency. And take note, for a pendulum to execute simple harmonic motion, so this angle has to be small. That is, let's say, less than approximately, let's say, 10 degrees. If it displaces too far, then it will no longer execute simple harmonic motion, because its motion will become more complex. The equations in this box, we're not going through the derivation because probably a little bit beyond the scope of this class, but these equations are derived based on the fact that the angle is small. If the angle is small, it's not small, then you cannot use these equations, because these equations will be much more complex. So that explains the simple in simple harmonic motion. Yes, somebody has the hand up. Can you unmute yourself and ask a question?
Yes, what is the symbol for the first equation that you have in the box? The symbol over the G?
L.
L, okay, I thought so, just make sure. Thank you.
So it's L over G. let me write uppercase L just to remove any possibility to misinterpret. And then here too, I'll do L. Okay, so bear that in mind when discussing simple harmonic motion. Now the next system we need to also establish the equations is the mass spring system. So we have a mass. And the mass, is free to oscillate back and forth. This mass has a value m, and it has a spring constant, okay? So every spring is characterized by a constant. So m, mass, k, spring constant. The spring constant is the number that characterizes the spring. It tells you how easy it is to stretch or compress the spring, okay? The ratio of the force to the compression. So springs with larger values of K means it takes more force to compress or to stretch it. Springs with a smaller value of K means those springs are easy to stretch or compress. So the smaller the value of K, the easier it is to stretch or compress the spring. The larger the value of K, the more difficult it is to compress it. So K is equal to the ratio of the force to the displacement. Okay, so for this system, the period is given by T equal to 2 pi square root of m over k. So again, the period of a simple a spring mass system depends on the mass and the spring constant, whereas the period of a pendulum depends just on the length and gravity. And since gravity is constant, it really just depends on the length, because that's the only thing that can change. So as you can see in this box, the period does not depend on mass. So that means if we are to construct two pendulums with different masses, one with a small ball, the other one with a bigger ball or sphere, as long as the lengths are the same, then the periods will be the same, because mass does not determine period for a pendulum. On the other hand, for a spring system, mass is a factor. So if you increase the mass, the period will increase. If you decrease the mass, the period will decrease. If you change the spring constant, then the period will also change. So take note of that. So period for a pendulum, you could say here, depends only on L. Okay, and then here depends on M and K. And of course, the frequency will be 1 over T, which is 1 over 2 pi. And then again, you flip the fraction and you have K over M. So you can say depends on M and K. And again, I'm going to put this in a box. So this, you really need to know just one of these equations because the other one is the inverse of that. So if you know the periods, frequency is just the inverse of the period. So these are not really four separate, equations. Okay, any question?
No.
Okay. Now, since we've started talking about the equations, let's look at the energy of a system undergoing simple harmonic motion. So the energy depends on the displacement, especially the potential energy. So at equilibrium, what will be the potential energy of a mass spring system? That's not a trick question. It's a straightforward question. What would be the energy when a system is at equilibrium?
0.
0, okay, that's correct. Why is it 0? Can you explain?
If it's at equilibrium, it's not in motion.
Okay, is potential energy related to motion?
No.
Okay, so you don't really need to talk about motion when you describing PE, right? Your answer is correct, but you need to have the right justification, and that's what I'm looking for.
Is it because the system's not disturbed?
Okay, potential energy depends on what?
Displacement.
Okay, it depends on displacement. So let's say x equal to minus a. Let's start with the negative amplitude. And that let's say x equal to 0, that's equilibrium. And then let's say x equal to plus a, which is the other amplitude. So let's consider this points. Okay, and I'm going to just to demarcate the different. Okay, so at x equal to minus a, what do you think? Will the potential energy be maximum, or will it be minimum, or what would it be? Remember in class, I mean, I don't expect you to necessarily have mastery of everything, but attempting the problem, definitely helps you, understand it better when the final answer is explained. So at 0, again, potential energy depends on how far you displace it from equilibrium. And I'm going to give you the equations. Maybe that will help, but you should have seen this, if you've reviewed the content. And that's why it's important to review, the content before the class session. So potential energy for a spring is 1/2 kinetic energy, the spring constant times the displacement squared. The kinetic energy is equal to 1/2 the mass times the velocity squared. So at the negative amplitude, your value of x is what? The amplitude is simply A, right? So let's say the amplitude was 10 units. So at the left-hand side, the value of x will be -10. And on the other side of equilibrium, the value of x will be 10, okay? So I'm just going to replace x here by -a. What is -a squared?
100.
What is -a squared?
A.
A.
What does it mean to square something?
Multiply it by itself twice.
Okay, so if we do -a times -a, what is it?
A.
A.
Think again.
-a squared.
Minus
Minus times minus is what?
positive.
A times a is what?
A squared.
A squared. Okay. 2 times 2 is not 2. It's 2 squared, which is 4. So a times -a times -a. So if we plug it in here, we're going to have 1/2 k into -a squared, which is just 1/2 k a squared. Okay. Does that make sense to everyone?
Yes.
So A here is the amplitude. It could be any number. So if the actual numerical value of the amplitude were given, then you just plug it in here to get the number. So that means at the other amplitude, since A is just positive, we'll have a potential energy of 1/2 ka squared. Okay. Now let's look at equilibrium. X is 0. When we plug in 0 in the equation for potential energy, what do we get? What is 0 squared?
0.
Okay. What is 0 times x times k?
0.
So that means when a simple harmonic oscillator is at equilibrium, it has no potential energy. But when it's at the amplitude, it has the maximum potential energy, which is 1/2 k times the amplitude squared. Now let's look at the kinetic energy. Kinetic energy depends on mass and velocity. So when an object reaches the amplitude, what is its velocity? When an object reaches its amplitude, what is its velocity?
It's his maximum.
What do you mean? Okay, explain. Why is it maximum?
As you said earlier, amplitude means that it's the max it could go.
Okay, so if something reaches the max it could go, what is its speed at that instant?
Can you say it again?
If something reaches the maximum displacement it can go, what is its velocity at that point? Zero, right? When you reach your destination, what is your velocity at that point?
0.
Zero. If it's not zero, then that's not the max. That means you have to keep going, right? So when, for simple harmonic motion, when an object reaches the maximum on either side, it stops and then reverses direction. Okay, so that means the potential, the kinetic energy at both amplitudes will be zero because V is equal to 0 here. Okay, so V is equal to 0 and V is equal to 0. So so that settles the extremes. Now at equilibrium, what is the can you describe the speed, how fast the object is moving? Remember, the object stops at the amplitude and then starts moving backwards. It passes equilibrium and then it starts slowing down and stops again at the other amplitude and then reverses, starts going back. Once it passes equilibrium, it starts slowing down until it stops at the other amplitude. So based on that description, where do you think the speed of the object is maximum?
At A.
You broke up. Could you repeat your answer? Your video, your audio broke up, so I didn't capture your answer. What did you say? This is open to the rest of the class. Okay, so what do you think? Where's the speed maximum?
Will it be at 0?
Why at 0?
Because you just said that it goes from one direction to another and it stops and goes another direction. So I'm assuming that it gathers its speed at 0.
Okay, and that's true because we know that the speed is 0 on the extremes, right? So if the speed is 0, that means it starts from 0, it increases as it goes to the left, but once it passes equilibrium, it begins to slow down and then again goes down to 0. So that means the maximum must be midway between the two zeros. So the maximum velocity will be at x equal to 0. So the kinetic energy here would be 1/2 m, and I'm going to put a max subscript to describe the fact that the velocity is maximum at equilibrium. Now, anywhere in between one amplitude and equilibrium, there would be a kinetic energy and potential energy, because in between 0 and equilibrium, you have a displacement and the velocity is not also 0. So you have two types of energy. But at the extremes, you have only one type. You have potential at the amplitude, and then at equilibrium, you only have kinetic, because at equilibrium, the spring is neither stretched nor compressed. Now, if we add these energies at the negative amplitude, what is the total energy? The kinetic energy is 0. The potential energy is 1/2 Ka squared. So what is the sum? What do you obtain when you add 0 to 1/2 Ka squared?
1/2 K squared.
Okay, so the total energy 1/2 Ka squared at equilibrium, 0 plus 1/2 mv max squared, you have 1/2 mv max squared. And at the other amplitude, you have 1/2 ka squared. So this summarizes the energy of a simple harmonic system, okay? The energy at equilibrium is entirely kinetic. The energy at the amplitude is entirely potential. And when you add the sum, the total energy is equal to the maximum kinetic energy is also equal to the maximum potential energy. Because if you add the sum at the amplitudes, you have 1/2 ka squared. At equilibrium, you have 1/2 mv max squared. Now, what do we know about energy? There is a principle you studied in physics 1 about energy. Who recalls the principle that governs energy? Mr. Bryson Williams, which principle governs the way energy evolves? Anyone, anybody in class can answer that? Or let me be more explicit and say, who remembers the principle of conservation of energy?
That energy can be converted, but not destroyed or created.
Okay, so energy cannot be created or destroyed, right? That's the statement. So that means as you go from the amplitude to equilibrium to the other amplitude, at all points, the total energy of the system must be the same. If the energy from one amplitude was different from the energy at equilibrium, that would mean that some energy has been created or destroyed, which is contrary to what is known. You know, the principle of conservation of energy is universally, established law. It's been verified experimentally. So energy cannot be created or destroyed. So based on that argument, you can say that the total energy at the amplitude, which is 1/2 ka squared, must equal the maximum kinetic energy, which is the total energy at equilibrium. Okay? So based on the law of conservation of energy, we have 1/2 ka squared is equal to 1/2 mv max squared. So from here, you can say V max squared. So the halves can cancel out. And if you divide both sides by m, you have k over m times a squared. And if you take the square root of both sides, you get V max is equal to square root k over m times a, because the square root A squared is just A. Okay, so take note. Take note, the square root doesn't cover A. It only covers K over M. So to emphasize that, let me put this in parentheses. Now, the quantity square root of K over M is known as the angular frequency or angular velocity. Okay, so this means that V max is equal to, if you replace the square root of K over M by omega, then you just have omega times omega times A. So V max is equal to omega times A. Okay, that's another equation you've learned today. So if they ask you to compute the maximum velocity for simple harmonic oscillator, all you need to know is the angular velocity, which is square root of the spring constant divided by the mass. Okay, so square root of the spring constant divided by the mass. That is your angular frequency. And then A is just the amplitude, which is the maximum displacement from equilibrium. Okay. Now, to generalize this, if we considered the object located at X, so at X different from 0, or let me use a mathematical term. If we consider the object at X so at 0 less than X less than A. That means if the object is not at equilibrium, is also not at the amplitude, then the total energy will be equal to the sum of the potential energy plus the sum of the kinetic energy. And saying that we've come to the end of the class, we're going to stop here, and I'll pre-record the explanations for the other sections on waves and sound intensity levels and resonance, and I'll post the notes and the recording in the lectures folder for module 1. So you review this with the tutorials, and then next week we'll just have a problem solving session. Okay, so you have a good rest of the day, and I'll see you in class next Thursday. Remember, this class section meets only on Thursdays. So Thursdays 12:30 to 2. The Tuesday period, you're going to use it to review the pre-recorded lectures, the tutorials, and all of the assignments that have been assigned in the class. All right, bye everyone.
Have a good weekend.
You too.
Dr. Natam,
Yes.
can I ask you a question regarding lab?